Real honor. Great to be here. You know, some history. When I was a grad student, I remember giving a talk here when the group was much smaller. And I remember walking into who was, I think, the chair at the time, Professor Farrar. I think you were chair back then, and dropping by and saying hi. So it's good to be back now, many years later. So let's begin. So this is one world line in my multiversal experience. You know, the work that I've done with Chern-Simons Gravity and Leptogenesis. I also think about other things, including some new ideas about dark matter. I look forward to talking with you all later on as the days continue. So now I need to advance. So one of the motivators for this is parity violation. Out of, we know up to 4 interactions, the weak interaction maximally violates parity. And my nice picture for this is this interaction, basic beta decay process is not, its mirror image is 100% not seen in the standard model. And the experimentalists, the theorists were not expecting this when, it was questioned. And so with that little bit of motivation and wisdom, one can ask a question. In fact, this is not how the story started, actually. The story started by asking different sets of questions. But if you backtrack, one can ask, well, what about gravity? Has that been tested? Has gravity been tested for parity violation? And so what one needs to do is to come up with a theory of gravity, a simple theory, the simplest theory possible in 4 dimensions that encodes parity violation. And I'm going to be careful when I say parity violation. I'm talking about in the gravitational wave sector. So one way we can think about this is that if I have a left-handed gravitational wave, parity takes h left to h right by a complex conjugation of the plus and cross polarization. But if I imagine I have new solutions, h tilde, which is some time-dependent function, h left. So some theory gives me some gravitational wave for tensor modes. If A of t is not equal to B of t, this parity transformation will not take h left into h right. And the theory I'm going to talk about generically does that. And so my pitch today, forget there's an HR over there. So observations made in the dark sector seems to suggest, or some people take, take that to mean that either in the UV or the IR, GR needs to be modified. Some people in this very room have worked on both sides of that problem. If this modification is parity violated, as we will see, there'll be observational consequences for cosmology, especially the early universe and particle physics, as well as astrophysics. And I'll talk about some of those today. We'll talk about such a theory, and we'll talk about baryogenesis and some new observational windows. So for my colleagues that have worked on this, who are more in the relativity community and who work with gravitational wave physics, they more look at this theory as some kind of like gadget or testbed to get them to imagine new ways of looking for parity violation in binary systems. So, one can argue that even if this theory is just utilitarian for them. All right. So I'm going to present the theory here. It's, if you look at it, the action is very straightforward. I will talk about 2 places where this theory descends from. The first is this theta is an axion-like particle. I just call it theta. It has a kinetic term. And this RR tilde is similar to FF dual in axion electrodynamics, but this is the Riemann tensor in this dual. And the field equations get modified if I include matter in this action. The difference here, this is just Einstein field equations with matter, but there's this new tensor which is the so-called cotton tensor. It includes things that look like, that have divergence of the Riemann tensor. And this term actually has some interesting structure in terms of encoding the parity violation. We also have just the fact that the R dual can source theta waves. And I want to talk about one way we can imagine how where this theory descends or ascends to, which is if I take a complex scalar. This is something like a gravitational Pechi-Quinn mechanism. I have a complex scalar, and there's a Pechi-Quinn symmetry of the following. If this scalar gets some vev at some arbitrary mass scale, depending on what that theory is, there is a pseudo-Navier-Goldstone mode that will couple basically to the chiral current, and by integrating out this triangle at that scale, I'll induce this term, which will come from this, this matrix element here. All right, this is what we normally see. And above this scale, now this will generate higher order curvature derivatives at, below this scale mu. But when I go to the UV, I go back to this theory. Yeah.
Are those coordinates 1, 2, 3, 4, and you have a, is there like any?
Oh, thank you. This is these are two gravitons of momentum with polarization E3 and E4.
Oh, okay. Oh,
right.
Thank you.
Okay. Thank you.
There's not a selected direction.
Yeah. So it's a basic triangle diagram. All right. So let's talk. Now I want to now that I've introduced the theory. There was another slide. The slide is at the end of this talk, where I can talk about actually, how this theory descends from heterotic string theory through the Green-Schwarz anomaly mechanism. If you want to hear about that, I can talk about it now. It's quite beautiful, and it sort of was the main reason. One of the main, back then when I was working on this problem, that's basically the place that, when Shalmet wrote that paper with Rukov. So I'm not going to talk about that because that's going to take some time, and I'll focus on some phenomenology. So let's talk about baryogenesis. Okay, the universe is dominated by matter or antimatter, but we need to make that quantitative. Actually, I want to just, it's kind of warm in this room, so, which is a good thing, actually. So the baryon asymmetry is quantified by the baryon asymmetry index, which is the number of baryons that one measures divided by either the entropy density or the number density of photons multiplied by the number of degrees of freedom, massless degrees of freedom, G star. Now, this quantity does not redshift because they both scale as 1 over a cubed, a being the scale factor. And this was measured directly in the CMB by WMAP by measuring omega baryon, but also BBN requires the number to be on the order of 10 to the minus 10 in the Saha equation. So, my favorite model of baryogenesis actually is electroweak baryogenesis. And I found it, to be fascinating. And some of us in this room have worked on electroweak baryogenesis. Looking at this paper, for example, which I believe stated that if you have a strongly first order phase transition, it is possible to do baryogenesis in the electroweak sector. Correct me if I'm wrong, if I was missing an ingredient there.
But that's what we said. I think
Right.
last time we figured out that entanglement with the gluon degrees of freedom actually, even if it's a strong first order phase transition, it doesn't work.
It doesn't work.
Sad to say.
Okay. But these were all interesting developments, and actually, as we'll see, the electroweak sector is still very important to do what I'm going to talk about today, which is leptogenesis. If there's an opportunity for me to get some water, I would be happy because I drank too much coffee this morning. All right. So I don't want to spend, but the basic point is that the reason why this is still important is that extensions to the electroweak sector that gives a first order phase transition can, for example, I can have a singlet, some extra singlets in the standard model, and those can also act as good dark matter candidates as well. these singlets can come in to make the electroweak phase transition in the Higgs sector first order, and that's interesting because you connect dark matter to the first order phase transition. There are other extensions. One of my favorite baryogenesis mechanisms, which is actually inspired, the one I'm going to talk about, is spontaneous baryogenesis by Cohen, Nelson, and Kaplan. And you'll probably see some variant of it. Thank you so much, Professor. So what's motivating this as well is that the question that I'm interested in is if I cook up a baryogenesis mechanism, and theorists can go and cook up many, can you find a way to test it? And so Chern-Simons Gravity provides a model of baryogenesis, okay? And we're going to talk about how it does that. And I want to walk through this very carefully. To understand how it works, we need to begin with inflation. This is a model that works naturally, no pun intended. You know, hint natural inflation, axionic inflation, things like that, with inflation. How does this work? Well, this is a typically money shot of inflation. The y-axis is a time scale. Inflation begins at some time, initial time, whatever the inflationary model is. The Hubble radius sets a divide between modes that are oscillating and modes that get stretched and frozen out. So if I take some mode, and this is the horizon scale, so some forward light cone, and if I take some perturbation in the horizon, within the horizon, and the action of inflation stretches this and freezes, so its oscillation freezes relative to the Hubble time scale. And if we look at some physical scale, this is now an expanded universe, say this is like last scattering, I can trace this scale back to this scale that was originated within the Hubble radius during inflation. So we can calculate this, we can calculate the spectrum of these modes. There's a scalar perturbation that we're all very familiar with, of course, and this will be related to the slow roll parameter if you were to now plug in a realistic potential for inflation. Then we also produce, Grisha taught us how to do this calculation, but you get this beautiful result with the Mukhanov variables that the tensor perturbations, its power spectrum is also roughly scale invariant depending on the particular model of inflation you're dealing with, but it roughly scales as Hubble over n Planck squared. And so, the spectrum of these perturbations are tilted to the red. So why is this relevant? Well, let's think about any model of baryogenesis. The electroweak phase transition, right, has sphalerone, non-perturbative sphalerone processes at the electroweak temperature that has baryon violating processes due to your usual ABJ anomaly, right? So there's a B plus L violation with the electroweak phase transition. So that's known physics to us. So, if you produce a net lepton asymmetry before that, a B minus L, for example, that would get converted to B. So what wiggle room do you have in cosmic history? Well, if you think to do this doing something like inflation, well, inflation will dilute any number density produced by 1 over a to the fourth or 1 over a to the cube if it's radiation or matter. So the exponential factor will just dilute that. So maybe reheating can do something. Or maybe something after reheating can do something to make your leptons. And that's the path we're going to take here. Before I go into the math, let's just talk about the idea. The idea is actually very simple. So there's one thing that happens that gives you the Sakharov conditions. I didn't want to spend time nailing out so let me just talk about the Sakharov conditions. You need all at once happen in 3 things. You need to produce your leptons. So you need a process that violates lepton number. All these things are loop suppressed in the standard model, so you need something that violates it. But at the same time, you need to bias, right, leptons production over anti-lepton production. So therefore you need CP and C violation to happen while this is happening. And this process must happen out of equilibrium. So inflation, what we're going to find, does this very naturally. The idea here is that within the Hubble radius, when inflation is happening, there's a CP violating phase that comes from an axion. Okay, and this sources gravitational waves that are chiral. What I mean by that is that there will be left-handed gravitational waves that couple differently in its phase compared to right-handed gravitational waves. We call this birefringence. This is not a birefringence as we find with the axion electrodynamics, where that birefringence happens with the dispersion relation, okay, of a plane wave. This is an amplitude birefringence. This is this. So the amplitudes differ for H left and H right. Therefore, it's a parity violated gravitational wave, and we'll see that soon. So the fact that you have a chiral gravitational wave, okay, that's the CP violation, that will source a gravitational anomaly. All right, that is to be distinguished from the RR dual in Chern-Simons gravity. It's separate. Okay, and the rapid expansion, the exponential expansion of inflation puts the system, this production, out of equilibrium.
And it's that, I think you call it theta, that's the origin of the original of CP violation. Is that right?
That's right.
If you would put that to zero, you would just...
That's exactly right. Thank you. And in fact, many years ago, Sophia gave a talk, and Alex Valinkin was in the audience, and he asked me the reverse question, and almost got me in trouble. So, meaning that it led to some problems. But the fact is, when that field, when inflation dies off, then this effect goes away. But let's talk about the effect. The key idea here is that the standard model has a gravitational anomaly. Okay, so this was, of course, done in Weinberg, Volume 2, but of course, the original, to my knowledge, calculation came in this paper. And the idea is that the gravitational anomaly could generate, no, if it's non-vanishing, will, according to this equation, generate a lepton asymmetry. Let's be more specific now. What this is telling me is actually, if I count my left and right-handed leptons and baryons, that's what this corresponds to. This is the chirality. It's plus or minus 1 for a left-handed or right-handed lepton and baryon. Right. So in the standard model, the only thing that is non-vanishing here are 3 neutrinos. Below, if you believe in the seesaw mechanism, below the scale of the seesaw mechanism of a right-hand neutrino. Okay, so this will be 3 here, but this is 0. In Minkowski space, if you had a Collider experiment or something, it's 0. In FRW space-time, it's also 0. But if I now use my typical perturbation of the FRW metric, it turns out what we're going to go after is computing this RR dual now in an inflationary situations with perturbations turned on. Okay. So if I just plug this metric into this, the only term that survived, right, is these terms here. Interchange left and right. And notice, if I swap left and right in this expression, I get 0. There's a symmetry of left goes to right, if left is equal to right. But if left is not equal to right, this is non-vanishing. That's a factual statement I just made about this term here. There's a minus sign, and if I do this, I get 0. But if I now look at the dynamics of a gravitational wave, when this scalar field, theta, is rolling, and this is my theta here, this is epsilon is phi over Hubble times m Planck, or some version It's a slow roll parameter, right? So if the scalar field in the Chern-Simons gravity theory is slowly rolling, meaning if its mass is less than the Hubble scale of associated with inflation, this is roughly a constant. And notice that the relative minus signs here, that's coming from this RR dual term that's sourced in the gravitational wave. Now remember, then I get this equation. The sign changes. The homogeneous part of this equation just gives me the good old-fashioned Hubble over M Planck square for vanilla inflation. But because of the source term, I get a new solution that gives me a growing amplitude for right or left, depending on your convention, and a decaying amplitude that's equal and opposite, as Glennis points out. So this is going to be the point here. Now I can use these solutions and calculate this. And I integrate that equation for del J mu in an FRW background, and I solve for n. And when I plug in those solutions, and it's outlined in the paper, you get this expression. And I want you to pay this. So this is the number of neutrinos that are produced by these gravitational waves, sourced by the rolling axion due to the action of theta FFR dual in using a gravitational anomaly in the standard model. And what we find is that there are three effects. One is basically the effect of inflation in amplifying the gravitational waves. The other effect is the effect of CP violation, which is related to phi dot, fixing a direction and a sign. And of course, we have this term that is due to a UV cutoff scale of the gravitational wave. And what we find is that if this scale, so the cutoff scale of my theory is the Planck scale, or close to the Planck scale. It could be the string scale if it's something from heterotic string theory. It could be this other scale if it's this progenitor theory of fermions. But let's make it, the Planck scale. If it's a Planck scale, what we find is that if this cutoff is less than 10 to the 16 JeV, this would be a JeV here, pardon me, or between this, I can get 10 to the minus 10. Yeah.
Good question. So 2 slides ago, you wrote the coupling for fermions. So is there a similar term for baryons, or?
This one here?
Yeah, but why do you single out leptons over baryons?
Oh no, it's both baryons and leptons. So this anomaly violates B minus L, U1 B minus L. Thank you for asking. But we have equal amounts of left and right-handed baryons in the standard model, so therefore this is 0 for baryons. The only thing that survives are left-handed neutrinos.
Oh, thank you.
Thanks for asking. All right, so yes.
In the formula that you had in the previous slide,
Yes, sir.
I see that there is a mu is the UV cutoff of your theory?
Of the gravitational waves.
So, but is this UV cutoff of, say, the quantum theory, or say something? Because I see that the formula goes on mu to the positive power, which means that looks like if it depends sensitively on the ultraviolet of the theory that you don't really control, right? Because you have a cutoff theory, so it goes to infinity, mu goes to infinity.
Yes, but going back to my argument, if it goes to the cutoff scale of the UV theory, we get back to this fermionic theory in that context.
Yes, but because when you have an effective theory, right? And so the effects that grow with the cutoff are something that happens near the ultraviolet.
Right, but in our case, we're like 3 or 4 orders of magnitude smaller than the UV cutoff scale.
Yes.
So the higher dimensional, from a Wilsonian perspective, I have all these other, higher order R terms. So if I'm well below the UV cutoff scale of that theory, of the effective field theory in this case, call it M, mu is 3 orders of magnitude or 4 smaller than that scale.
So again, maybe I didn't understand what is mu then. Mu is not the cutoff of the theory?
No, it's not a cutoff. I'm producing gravitational waves. They're classical.
Okay, up to a scale mu.
Up to a scale mu. Thanks for asking. Yeah.
So you mentioned you use baryogenesis during the inflation. So I'm just wondering whether why the inflation doesn't wash out the Baryogenesis.
Oh, very good. That's a great question. Thanks for asking that question. Yes, this is actually surprising. We weren't expecting this, but the math. Notice this is the active inflation, 1 over a cubed. They're producing leptons, but the anomaly production has an a to the 4th growth factor. All right. So but that's exactly why you should not expect it. But so this was done. This was redone. This calculation was redone by by Rob Caldwell, and then Peter Atzhead and Andrew Long. They kind of started playing with this idea some more, and because there's an assumption I made that no one caught me on, which was that when the inflaton dumps its energy into radiation, so-called reheating, I assume that the reheating is spontaneous reheating. Okay, and if reheating is not spontaneous and more gradual, the effect actually, the number production goes away. It becomes less and less effective. So one of the things that Peter did was he included more realistic reheating mechanisms, and this is a parameter space for this particular leptogenesis mechanism. And what they find is that this is the Hubble scale, and this is a reheat temperature, and you see that this number can be accommodated even when I go to more realistic reheating mechanisms. Then Rob Caldwell came to the scene, and him and his student. Well, that was interesting because when I was at Dartmouth, Robert was very, he was critical of what we were doing, and then eventually he got around to writing a paper about it. And in that paper, they did something even more remarkable, as far as I'm concerned, was that they found that this UV property went away if you included, along with the axion coupled to R dual, it couples to some gauge sector, FF dual, if the gauge sector is non-abelian. So if I have a dark gauge sector or even a visible gauge sector, if it's operating, for example, is being excited during inflation, the number density that one calculates loses the UV dependence. And what they did was they related, and we anticipated that when Michael and I and Shaheen wrote our paper, we ended our paper by saying it's really interesting that the number density is scales with delta rho over rho of the gravitational wave of inflation. But what they did was they actually showed that this tensor to scalar ratio associated with this mechanism does two things. It produces circularly polarized V modes of tensor perturbations during inflation. That's the first thing. So it's not just a B mode, but it's actually a VB mode, and I'll tell you more if you want to know what the difference is, really, and the similarities are. The B mode is a vector mode, but it's a vector mode that has circular, has helicity polarization. But what they found was actually, this thing actually has that has a lower bound that's 10 to the minus 2, and I was talking to Brian Keaton the other day from the Simons Observatory, and he goes, this is actually really interesting because the spectrum of such gravitational waves, this is BB. What these waves do is generate a TB cross correlation, temperature B mode, and it's about an order of magnitude larger. And so this is something that the Simons Observatory will be going after for. They have a clever way of dealing with the leakage between T and B modes if you're trying to look for birefringence. So there's a very slick way they have of actually being able to look for such modes, but I promise to not reveal that. Well, I don't know if I promised to not reveal, but I assume that was, I guess it was very slick, but it isn't like there's any competition, right? Anybody else working on, okay. It has to do with drones.
We'll cut it out of the recording. We'll cut it out of the recording.
Okay, thank you very much. So they use a drone to calibrate. All right, there's a bonus here, because one of the things I always worried about with reheating was you have to couple the inflaton to the standard model with the amount of degrees of freedom, so it decays. And I never liked that. It was this extra fine tuning. I didn't like it. But we can rely on the equivalence principle here. because the graviton, the general relativity, you know, the connection speaks to everything, right? That's the equivalence principle. So here's what's really interesting. Take this mechanism, wait till reheating. The axion field, if the axion field now, this is just a bonus, is the inflaton, such as an axion inflation, you know, during parametric resonance when the inflaton field is oscillating rapidly, right? So when it undergoes this type of oscillation, you induce a Matthew-like equation for this gravitational wave because of the same phi RR dual coupling. The right-handed gravitational wave will get amplified, right? And this is basically a parametric Matthew-like equation. Okay, and this is a plot basically on the time scale, you know, related to the mass of that. So if I have rapid oscillations of mass scales much smaller than the Hubble time scale, then I can have rapid oscillations. And then what you find is when you couple any matter field that you're going to produce in like the standard model, it will universally couple to this oscillating gravitational field. And when you look at the log of the number density, and that's basically that what we call a broadband parametric resonance to compare with the usual Matthew equation that one gets in the parametric resonance that Jenny Trashin and Robert Brandenburg and Andre Linde and company and Lev Kaufman found. Okay, so that's a little bonus, and that's really interesting because somebody who's going to be hanging out with you all soon, Cyril, and I are working on we're going to use this to basically constrain baryogenesis mechanisms of this type by looking at the back reaction during parametric resonance that could induce potentially compensated isocurvature perturbations. I don't want to spend too much time. I can talk offline about that because there's more to cover in this talk. So just some future prospects. Going back to your question, it's something I am thinking about. For example, if I do quantize these gravitational waves, then I have to really think about what your question is. And you know, if you think about this in the context of how the heterotic string theory naturally gives you in 4 dimension this theta FF dual, if this is a universal axion, for example, then I'll get the theta phi will couple, or theta, will couple to FF dual and RR dual, and you know, this FF dual was exactly the piece that Caldwell and company considered. So one of the things we're thinking about is in the gravitational wave sector, what happens when you turn on both and you have them crosstalk, whether or not you're going to see a more interesting signal. So axion electrodynamics with theta RR dual, and you have a dilettante speak to the two of them. And you know, this is a little, you know, how does this fit into the string axiverse? We have some people here that, what happens if I have many axions around with many of these couplings? What are the consequences? Now I want to move into, how much time do I have? Because
yeah, I think we started a bit late, so maybe go to 3 or 5. That's good.
okay, what's the time now?
It's the clock's there.
Hold on. All right, cool. So part 2.5 of the talk is I'm going to talk about some work done with somebody else in this room. And so, you know, one of the things I'm most proud of is, you know, get to a point in life where your first grad student is doing much, you know, is much more, you know, it's like a real leader in the field, and then you're following them. And that's my student, Nico Yunus, who's now the director of the Theory Center at Illinois Urbana-Champaign. And him and Franz Pretorius took this Chern-Simons Gravity. This is an example of, like, you know, the relativists who said, okay, this is a theory I can at least play with. It encodes parity violation. What do Kerr black hole, Kerr-like solutions look like? And let me also say that Nemanja Kaliper, actually, him and Keith Olive, many years ago, actually, were already looking at such corrections. Like they were asking the question, can black holes have hair? And the answer is, if you modify general relativity, then those no hair theories get relaxed, and they actually saw a similar structure, but it was like 20 years before us. And so, you know, what can I say? It's Nemanja Caliper. He's smarter than me. So, yeah, so let's go back to this. In a nutshell, the Kerr solution gets modified. So this is the Kerr line element. But then you have basically what can look like the axion field coupling to the rotating of frames, okay, in a Kerr black hole. So you have a d theta d phi piece, and you know there's a very long paper with lots of calculations in it. But the takeaway is that if you look at this solution and say, well, how does it really differ from the Kerr black hole? Is that the causal structure changes. What do I mean by this? Well, remember in the Kerr black hole, you had this ergosphere, okay, which is actually very useful for things like superradiance. But what we also discovered that does not happen in ordinary GR and with Kerr black holes in general is that you have these cap-like regions, which extend to about 20 degrees from the North Pole and the South Pole. That's what these caps are supposed to represent, where the focusing theorem, if I look at two null or light-like geodesics, instead of focusing on the collapse of ordinary matter, they defocus. It turns out that these regions have defocusing, and actually there are no issues, there are no, what's the word? Starts with the word P. Plagues, or there's a word for this. So we find no naked singularities. The solution is stable. This was the Prechoris paper that showed that the solutions are stable against perturbations. But it breaks isospectrality, meaning the way between the axial and gravitational perturbations. So what that means is that the gravitational perturbations actually, in terms of the production of, this is in the case of superradiance, what happens is that you have odd parity modes that can carry more power than even parity modes. Whereas in ordinary Kerr black hole, the spectrum between even and parity modes is the same. So we're still looking at this in the context of seeing whether or not these caps can have observational effects in the context of fermion production and wormhole solutions. And so this is a good thing. I give a lot of credit to my student Leah Jenks, who really, impressed us with her powerful skills. So now so now that we have these rotating black holes, what can you do with this? I kind of want to give a little pedagogical slide about the chirp mass and how we think about this. So what we do is we want to study the gravitational wave emission from two compact binaries separated by some distance a, and they're rotating with some angular frequency omega, F. So they're rotating around each other, and this rotation, according to the perturbed Einstein equations, if I now work in what I call a post-Newtonian approximation, which means that I use an expansion parameter above the gravitational potential, that basically an expansion in the velocity of this orbital system compared to the speed of light, it's much less. V over c is much less than the speed of light. So I expand the gravitational potential, right? And so what I call 1pn corresponds to v squared over c squared. 2pn is v to the fourth over c squared, and I expand in terms of that. If I actually expand this equation in terms of that, I end up with this equation by solving the Greens in terms of inverting the operator. And what this tells me is that this the gravitational wave emission is sourced by the quadrupole moment of the masses of these two compact bodies. It's rotating. It's going to now source gravitational waves, which will be emitted. As it emits the orbital energy, A is this distance. As the distance increases, I can lose energy. And there's a so-called balance equation that tells me that the luminosity of the gravity waves emitted, right, is related to the rate of change of the orbital energy. And then I can actually solve by using Kepler's law to give me the solution of this infall. And notice that it scales with this thing called a chirp mass and the effective mass, reduced mass. And then I can then use this solution and get the frequency. And that goes as this chirp mass to the 5/8 power and the time it takes for the bodies to coalesce. And when we can use that to read off the phase information in general relativity, and these 7, 6, and 8s have to, well, we can go into more detail, but I just want to give you a quick review, because we're going to use this now to talk about how Chern-Simons gravity could impact the phase information here for these rotating black holes. I'm going to skip this slide because I'm running out of time. So Masha, there's some more slides here. Yes. There's another effect that we looked at that had to do with amplitude birefringence. If we're looking at a binary system from far away and the gravitational waves are propagating to us, there's this amplitude birefringence that happens now with, if this xion field is like some huge cloud, right, that passes through, it's actually going to create an amplitude birefringence, and that changes basically the inclination angle between the observer and the plane of the binary. And so Masha and her colleagues wrote a beautiful paper recently using this effect and the latest data to constrain this observation. So that's just an advertisement. But what I want to talk about now are systems where I have black holes that are kind of solar mass, 40 solar masses on that order. And what you find, remember, the larger the chirp mass, the faster the system coalesces. So if I have, black holes in the order of like 300 kilometers, right, 40, 50 solar masses, they can have a long in-spiral phases for hundreds of cycles before they coalesce. And I'm only going to be looking at this in-spiral phase where I can trust this PN approximation. So here's a nice little picture of, well, I guess that animation's gone. Oh, I guess the animation's gone. All right, this is going to be my last few slides. So I'm going to slow down a little bit and drink my water. So this is not 3 black holes, meant to be a picture of 2 black holes, and then it's kind of rotating around. Okay, the bad arts in me. So as I said, there's a scalar dipole, magnetic fall off of the scalar cloud around the black hole. That's what that picture is supposed to be. They're going around each other, and then they will emit gravitational waves. But what you find is that the scalar field induces induces a spin-spin and a spin-orbit interaction, because the scalar field is long range, right? It's a massive scalar field, roughly massive scalar field, and it will emit scalar waves as well, because in a far zone, the scalar field couples to the delta function source due to the motion and the acceleration of the black hole. But that's a subdominant effect. The dominant effect will be that there'll be a phase shift the same way the 1 PN thing from, the orbital energy gets modified to 2 PN. That is calculated. We find that there's a dipole interaction due to the spin induced by the scalar field. And calculation was done by my academic grandson, I guess, the Yagi, Yunus, and Tanaka. And what they find was that this change in the phase due to the change in the binary, induces, so A, B, and C are numbers on the order of 1. They're like long numbers though, but I want to just make the order of 1. and you have a spin orbit. So the system what we have now is we have a binary, we have spins that are not aligned with the orbital plane for a good reason. You have the orbital angular momentum, the spin, and what we can see is that it induces a spin, spin, spin orbit, spin orbit, spin orbit coupling, and this creates a 2pn. These are the mass of the two black holes, and this is the reduced mass, eta. And what we find is that this induces a phase shift above GR, and it is degenerate. In general relativity, just good old GR with a binary system with spin, right? You actually induce spin, spin, and spin orbit interactions as well at 1.5 pn. But it also changes the amplitude of the gravitational wave template. So I construct a theoretical template. The amplitude of the gravitational wave will also vary as a function of the spins. And so if you can pin down that measurement and the amplitude, then you can actually go after this term and lift the degeneracy. And so I want to kind of show you. So Nico and I wrote a paper in 2018 where we said, okay, given this type of system, what's the ideal system, binary system, to see such a signal? And I'll tell you what a signal might look like. So as I said, there's a degeneracy between the parity violation, meaning the induction of this scalar here that couples R dual, and its impact on the binary system, and the spin. But the degeneracy can be broken if the spin magnitude is extracted by the amplitude modulated binary black hole binary. This is not my pay grade. If you're interested in knowing the details of that, invite Nico out here. Or the observation of a spin and neutron star black hole binary. So these are the two ideal systems, but you need spin processor. All right, so I'm going to end now with some what I think to be a clever way, and it uses some intuition in music, which is one time I was asking somebody, a student, I said, "What's a beat?" What's a beat? You hit a drum. I was like, no, you don't even know what a beat is. A beat is if I have two very similar frequencies and I subtract them. The additions of cosines subtract to a sine. And so notice that this tiny little phase shift, if I actually evolve this over very, very long periods, and I then create a template, right, that gives me a best fit to data, assuming that it is Chern-Simons gravity, and I subtract it from a gravitational wave template. The idea is that would be the signal in the ideal setting, of course, is what I'm about to show you here. And that you can actually hear it. What is it, volume?
It should be. Yeah.
Oh, I see, but it's feedback. Oh, it's a shame.
I can turn off this. Sorry, no, you can't.
Okay, so what I'll do is
Mute you, please.
but I won't be able to hear.
Yeah, I'm not sure if I could.
This is the best part of talk.
Just mute him and then play it, right?
Mute the room.
He wants to talk. Yeah, so they want the.
I'm not going to talk. I'm going to shut up. I'll be quiet.
Hear him for a moment.
Sure. for questions.
I had a question about the first part of the talk, or next talk, thank you.
Yes.
You were mentioning that you get the compensated isocurvature.
Yes.
And I was wondering.
No. Well, I'm saying that thanks for that. I didn't mean to cut you off, by the way. We are hoping to get that.
My question was if you could say a comment on what exact mechanism you're thinking will give rise to isocurvature in that scenario?
Yes. The idea here is that so this part is going to come not from Chern-Simons gravity because we haven't explored that yet, but it's going to come from the fact that H, right, is going to couple to. So we have this amplitude where H is basically coupling to the matter field. So I want to write this as phi squared or something. Right? And this production mechanism. So if you think about the decay of H into this phi, H has a lot of amplitude. That's why it has to do that, right? It's being parametrically amplified. And the idea here that this is, if phi is a visible matter species, and then we call this phi b, this can be fermionic, whatever, this being structural here. But H will likewise couple to some dark sector. I'm going to call this psi dark, right? That compensated isocurvature means that the delta rho of 1 times, rho of baryon and rho visible, and delta rho visible, rho baryon, right, that this is 0. But this is an isocurvature perturbation because it's a perturbation in a matter field, matter component. So it's like an entropy perturbation. So that's a basic idea. That's what we're not, we're like in the middle of learning this stuff. There was no way I was ever thinking about compensated isocurvature, but Cyril was the one that brought that idea to me.
Thank you.
You're welcome.
I have two questions. The first question is your Baryogenesis mechanism depend on the concrete mechanism of the reheating, or
Concrete mechanism of reheating.
Yeah, because you show a plot like the H and the.
So if you compare the parametric amplification, that ordinary, if you go back to Brandenburger Trashing, and we compare that log plot that we had, it's similar. I don't remember the exact similarity, but I think it's in that sense we're saying that it is a similar mechanism, but we don't require a direct coupling between the inflaton field and the matter field. It comes free.
I'm sorry, I still don't know. You mean it's insensitive with the reheating mechanism?
So what I mean by reheating is the precursor of what I call parametric resonance, parametric production, explosive production of particles due to the oscillation of the inflaton field. So it's the same idea here, same exact idea, except the thing that's generating the part of the production is the rapid oscillation of the gravitational field.
So you don't need an extra reheating mechanism.
We don't need extra. Thank you. We don't need extra reheating mechanism. Well,
and also my another question is, since you have mentioned the gravitational wave is it's parametrically enhanced, so will they leave some remnant gravitational wave, just the signal which will be detected?
I don't have much feeling, much intuition for the stochastic gravitational wave background and how this might impact that. But I do know that in the Caldwell paper, he did discuss that. But it was kind of went up.
I have a question, but I don't know about this. But maybe kind of following what Mastin was saying. So we have this error dual, but then in gravity, many different tensors have the same order in an EFT expansion. If mu square goes in the numerator, how can we be sure that the other terms that are higher in power of curvature should not contribute more to your equation?
Just to be sure, if I have say r square, pi over r over m, then I have some, some r to the n and some higher power rn, right? That's e minus n. These higher order terms, so if I'm generating a scale that is less than this scale, these terms will be irrelevant. It's a usual Wilsonian story.
Yes.
As long as the cutoff scale of the cutoff scale of these gravitational waves is, much less than the cutoff scale of the theory M.
Okay. Okay. So again, so mu again is, yeah, I'm correcting myself. So mu again will not tell
Mu is
me.
not M. Yeah.
Yes. So mu, even though mu appears on top, this is not telling me that it's dangerous to add more terms in the Lagrangian.
That's right, because it'll be suppressed by the
Anyways.
UV cutoff scale of the theory M. Now, I don't want to bring up your issue, but that's something to think about.
I had a question too. So you talked about dynamical Chern-Simons in sort of early universe cosmology, inflation, and then black holes. So is it for the same type of parameters that you get observable effects, or different ones? So is the coupling of the xion to give you baryogenesis the same as?
Oh yeah, I forgot to mention there is a nice paper I think Asher Berlin wrote on some people called axiogenesis, where they directly produce leptogenesis from an axion FF dual coupling, I believe. I think that's what you might be asking.
No, I'm just asking. You have the dynamical Chern-Simons theory, but to get observable effects in black holes as well as leptogenesis, is it the same?
No, very good. Thanks for asking that question. That was Matt's question. So what we're kind of imagining is that there are two types of theories, right? One is this theory, something that comes from heterotic string theory, right? We get this from the Green-Schwarz mechanism when we descend down to the four-dimensional complexification. And I know that Bobby is very happy because you taught me this many years ago. I don't know if you remember that. He's one of the people that taught me that. But the other one, that's a high scale. That's 1 over n string, for example, right? But the other one is the one that we can think about coming from this fermionic progenitor theory that uses something like how the pion arises from QCD, the pion electrodynamic, and the eta particle FF dual, which is the integrate out.
So you need a lower cutoff.
For that, you need a lower cutoff, so you can have a dark, like some hidden sector. But what you need a hidden sector that doesn't couple to the standard model at all, right? And so the scale that this scalar field generates a mass is very low. The mass scale is very low, right? So if you had such a hidden sector, then you could have a mu that's tiny.
Okay, there's no more. Well, let's thank Stephon again for the review.